In 5.2, we're restricting our focus just to look at two different kinds of segments, and that's perpendicular or angle bisectors. First question, we might look at this a bit in class together, but we're going to skip through it and just basically look at our first definition, which is our perpendicular bisector theorem. And what that says, if a point is on the perpendicular bisector of a segment, so any point on that perpendicular bisector, then that tells us it's going to be equidistant from the endpoints of that segment. So in that first situation, if I know that PM is perpendicular to AB and also that AM is equal to BM, so if it's perpendicular and also bisecting segment AB, what that tells me is this point up here, since it's on the bisector, it's going to be the same distance from one end of the segment as it is from the other. So I know that distance from P to A will be the same as the distance from P to B. We kind of already saw this already when we were talking about isosceles triangles. If I cut this vertex angle in half, remember that would make it isosceles with these two legs being equal. Saw something, that was similar in that last section. So anytime I have a perpendicular bisector, if I take any point, again I could move this point up or down as well, the distance from that point to one end of the segment will be the same as the distance from that point to the other end. If I look at that again, we can actually talk about the converse as well. So the converse, again, just means that we're flipping a statement. If a point is equidistant from the endpoints of the segment, then we also know it's on the perpendicular bisector of that segment. So I can take what we just saw and reverse that. We'll still have our rule apply. So that tells me if I know that PR and PT are the same length, so if I know that distance from one end of the segment to the point P is the same as the distance from the other end to point P, what that tells me is it should lie on that perpendicular bisector. So that point P here that we saw should be on the line of your perpendicular bisector. So PM would be perpendicular to AB. So those two are going to be perpendicular. And also AM and BM are going to be the same distance, again, because that segment was being bisected. So if I start out with the two distances being the same to the ends of the segment, that segment is a perpendicular bisector. So the way we actually use this in most of our problems is going to be a little bit simpler than how it looks maybe. The first problem, we have to find the length of QR, which is this length that's given 5n minus 7, and the other segment on the other side is 3n minus 1. We know these two are equal because, again, if I start with a perpendicular bisector, then that means the point up here, Q, is going to be the same distance from one end of the segment as it is to the other. So from Q to R should be the same as from Q to P. Means I can make this equation, 3n minus 1 should be equal to 5n minus 7. All we got to do is isolate and solve for n. We get that n is 3. And once I know n is 3, since I want to get the length of QR, I can take that and plug it back really into either equation since they should both be equal anyway. But 5 times 3 minus 7, that should give us 18. Or sorry, that's not 18, that should be 8. So that's a mistake that I'll have to fix. So 15 minus 7, is just going to be 8 instead. If I'm looking for the length of RT we find basically the same way. Since I have the same starting information, I have a perpendicular bisector, I have a point T here that's on the bisector. That means the length from T to one endpoint should be the same as the distance from T to the other end. So 10x minus 3 equals 5x plus 2. That means if I solve here, I get that 5x is 5. So when x is 1, all I got to do is plug that back in. 10 times 1 minus 3, that should give us 7 for the length of RT. So let's try and use that perpendicular bisector again, and this time I have basically a word problem or a little bit of a description. A director of the park at the right, or I guess on the below, wants a t-shirt stand built at a point that's equidistant from the spaceship chute, so this right over here, and the roll-in coaster, so right over here. And if I want to find the possible locations that would be equidistant, one way to do it would just be to put it halfway in between the two. So I could put my t-shirt stand at the midpoint. Or, based on what I know about our perpendicular bisector, is I could also put that point t-shirt stand on any point that lies on your perpendicular bisector. So I could go further this way, I could go further that way. Basically what I did there is label a bunch of points that we could use to put our t-shirt stand. So it could go right in the middle, or I could go below or above that line as long as it lies on that perpendicular bisector. And next question is really saying the same thing, just using two different points. So now instead of the spaceship chute and the roll-in coaster, it's looking between this chute and the paddle boats. So if I want to put that t-shirt stand between the two of these, again, I could put that t-shirt stand in the middle on the line between P and S. Or if I go on that perpendicular bisector, I could go below or above. So I just said that it could be any point on that perpendicular bisector that bisects the segment from P to S. So next what we're going to look at is the distance from a point to a line. So that's the perpendicular segment from that point to the line. So again, anytime you're doing a distance, you want a straight line, so you want to make it perpendicular. Distance is also the length of the shortest segment from that point to the line. So again, that's the shortest way to get from one point to the other is by taking that straight distance. If a point is on the bisector of an angle, what we know is that it's also equidistant from the two sides of that angle. So if I see this point right here, S, I know that it's on the angle bisector because I am told that QS bisects angle PQR. So I have that circle right here. We start off by knowing that this angle is bisected. And also, if I'm taking that perpendicular distance, that should be the shortest distance. And what this theorem is telling me is that since S is on the angle bisector, that means the distance from S to one side of the angle, so from distance from S to P, should be the same as the distance from S to the other side of your angle, so from S to R. And that's what we have in that second figure. So PS and RS should be the same length. Also, for the converse, remember converse just means we're flipping that rule. So this time, if I know there's an angle in the interior, so still looking at S, if I know it's the same distance to both of your sides, so again, kind of like what we finished with in that last part, if I know the distance to each side of that angle is the same, I know that point S would have to lie on that perpendicular, or sorry, not perpendicular, it would have to lie on that angle bisector. So if I have angle PQR, S is going to lie on that bisector QS because, again, it was the same distance to both of those sides. So just like with any other converse, again, I could use that rule one way. I could use the fact that since it's on a bisector, it's going to be the same distance to both sides. Or if I flip that, if it's the same distance to both of those sides, it should be on the bisector. So again, using that rule is usually a little bit simpler than kind of stating the rule. So if I'm just trying to use that here, we have to find the length of RM. And basically all we have to set up is that since this is an angle bisector, I see that down here, angle MNQ is being cut in half. Since that is an angle bisector, that means from R to M should be the same distance as from R to P. So all I got to do is make sure 7x and 2x plus 25 are equal, solve for x, and then since I'm looking for RM, I take my answer for x and I plug it back in. So 7 times 5 should be 35 for that length. If I try and do that again for that bottom question, again, same idea. If I know that this is an angle bisector, so CF is cutting this angle right here in half into those two parts, that means the distance to both sides should be the same, so 6x minus 3 should be equal to 4x plus 9. Set up that equation and solve for x. We get that x is 3. Once I know that x is 3, same as with the other one, I can go back, plug that in. 6 times 3, and for whatever reason, yeah, I guess that's plus. It looks like a minus there. But yeah, 6 times 3 plus 3 should give you 21. So if I'm looking for that length, again, it should just be the same to each side of the angle. So let's also start 5-3. You might not get all the way through it, but at least we can start looking at bisectors in our triangles. And there's a few different ways we could have bisectors, and the first one is looking at, well actually before we even get into a bisector, let's define some terms. We have when 3 or more lines intersect at a single point, we call those concurrent. And the point which they meet is the point of concurrency. So again, it's a little bit tougher for 3 lines to meet than just 2 lines. But if I look at this example here, it looks like XP, YP, ZP, they all meet in the same point. That would be a point of concurrency. So that point in the middle of our triangle is what we're looking at in terms of our definitions. So in the first way we can have those lines meet, we can have concurrency if I look at perpendicular bisectors. So if the perpendicular bisectors are the sides, so for example, PX is the perpendicular bisector of AB. We also have PY is the perpendicular bisector of AC. PZ is the perpendicular bisector of BC. If I'm trying to find the points where those all meet, so perpendicular bisector, bisector, and bisector all meet at point P, what we know about that point is it should be the same distance from all 3 vertices. So again, your 3 perpendicular bisectors, XP, YP, and ZP. If I want them all to meet, what that's going to mean is that the distance from each point, so from A to P, distance is going to be the same as the other vertex, from B to P, or from C to P. All those lengths would be the same. And what we call that point where they meet, so all the perpendicular bisectors meeting at that point in the middle, we call that for this situation a circumcenter. So circumcenter is the equidistant from the 3 vertices. We saw that with that last rule, so distance from any of those points of the triangle should be the same. The circumcenter would be the center of a circle that contains each vertex of that triangle. So this is where the name comes from. if I drew a circle around that triangle, and we call that circumscribed about the triangle, I'm drawing that circle around your figure so that the triangle fits inside the circle, I can see that the distance from each vertex to the middle of that circle would also be the center. So we're basically just using 3 radii. The circumcenter of this triangle can be inside, on, or outside a triangle. It kind of depends on what kind of triangle you're using, if it's acute, right, or obtuse. So in that next question on the back side of this, we look and see an example where I think we have a right triangle. If we're trying to find the coordinates of the circumcenter, if the triangle has these vertices, 2, 7, 10, 7, and 10, 3, I follow these steps, and this is what my figure looks like afterwards. And again, first we start by labeling our coordinates, A, B, and C, according to the problem itself. And then the next thing we're going to do is find the midpoint of those sides. So it's easy if they're just going left or right, or just up or down. We don't have to use the distance formula. What you could do, if x is going from 2 to 10 here, and we use the same y value, halfway between 2 and 10 is 6. So this point up here for the midpoint should be 6, 7. Same kind of thing here. If I'm going from a y of 3 to a y of 7, halfway in between the y is 5. So I know this midpoint is going to be at 10, 5. And as long as I draw the perpendicular bisectors, again, it should be going through those midpoints. So I've just got to draw a line that's perpendicular. What I see when I draw those perpendicular lines from the midpoints is that they both meet here at 6, 5. So they both meet at the same place. And notice for a right triangle, those meet exactly on the hypotenuse of that right triangle. So we didn't see it last time. They met inside the circle, but inside the triangle. This time they're meeting on the side of the triangle. So circumcenter would be 6, 5. Trying that next one, this is just looking at where we would be placing our planar. If we want to put, a bench that's equidistant from the 3 trees, we should place that bench, again, just based on the definition. If I treat all 3 of those trees as a vertex, the bench should be at the circumcenter. So if I took all the perpendicular bisectors and find the point where they meet, the circumcenter is going to be the same distance to each vertex. So the distance to tree A, tree B, and tree C, it would all be the same as long as I use that circumcenter. So trying this again with, same page, last page. Trying this again, we're now looking not at perpendicular bisectors, now we're looking at where angle bisectors meet. So it's a little hard to see in that figure, but we have some distances drawn in there. Again, these aren't necessarily bisectors because those wouldn't be the same distances. But now I'm looking to bisect not the sides, I'm looking to bisect the angles of that triangle. And what they meet is a point that's concurrent, that's equidistant to all the sides. So it's kind of flipped. Last time we saw the sides were being bisected, so distance from every vertex was the same. Now the vertices are being bisected, so A, B, and C, we're cutting those angles in half. And what that means is your length to each side, so here, here, and here, those should all be the same length. So kind of draw that in a little bit sideways, but XP, YP, and ZP should all be the same length, since I'm breaking up and trying to get the concurrency that goes between all 3 sides the same. So the point of concurrency, this case we call it an incenter. Remember last time it's circumcenter because it's circumscribed within that circle. So incenter, we want to remember incenter because basically if I draw a triangle inside, a circle inside that triangle, it's always going to be in the center. So if I have X, Y, and Z, so if I have these distances are all the same, again, the point where these meet is going to be a circle that's within your triangle, not like the last time where we had a circumscribed triangle outside the outside of your triangle. So looking for this using a couple of examples, again, we use it kind of like we did before. The rule itself, I think, is harder than the actual examples. If I know that GE and GF are both given, so 2x minus 7 and x plus 4, as long as I'm using the angle bisectors, that just means the length to each side should be the same. So if I'm trying to find GD, even though I don't have an expression for it, I could set the other 2 equal. So distance from the center to one side should be the same as the incenter to the other. So 2x minus 7 should be x plus 4. If I solve that, I get that x is 11. So that means that if I'm looking for GD, I can just take 11, substitute it into either one of those expressions, and it should be the same thing. They should all be basically have the length of 15. So don't really have enough time to look at that last one, but just to kind of keep this under 15 minutes, we set up the same kind of question. Just make sure that these 2 are equal. Distance from Q to N should be the distance as from Q to M. They should both be equal. And that means I set them equal, solve for QO, should get 61 for that last one. So make sure you come in with questions for 5.2 and 5.3. Try and get both of those done with the practice in class.